So thank you. All right, so hello, now that I remembered to record, we're talking about oxidation reduction, and we're gonna first talk with this simple equation, and we're gonna be writing half reactions. So you just pull out the elements that go together, so the chromium 2 to the chromium 3, and then the I2s to the 2I. Keep things on the same side of the arrow as they were initially, and you always first, for little notes here, kind of a guideline, you balance the elements that we learned since way back in chemistry 221. So the chromium was already balanced, but the iodine, we would need a coefficient of a 2 there. And then this step 3 that I tried to hide, oh, no, sorry. This step 2b is the piece that is new, which is the charge has to be the same on both sides. And you do that by adding electrons. And so on this one, electrons have a negative charge, remember, you all know that. For this first equation, with the chromium to be balanced, we have to add an electron on the product side. So then we have a +2 here, +3 minus 1 gives us a +2. So each side of the arrow has a +2. In the iodine equation, the I2 is a solid, it's neutral. So to balance the 2 negatives on the product side, we would add 2 electrons to the reactant side. So that is really the new piece. One is pulling it out into the 2 half reactions, which is actually easier than well, it's kind of like the half reactions we did with the KSP, if you remember, when I had 2 different precipitates. It's adding these electrons. Now, the equation, one of the half reactions always is losing electrons, and one is always going to be gaining. And we're going to get to that when we talk about oxidation reduction. But it is something I want to mention that will help you to know if you're doing the electrons right, because if your electrons ended up on the same side for both equations, that's not possible. So somewhere you have something off. All right, the other new piece is this step 3. Before we bring the equations together, the electrons have to be the same in both equations. And so we're going to have to multiply by some factor, so the electrons have to cross out. The electrons are never, ever in your final equation. So to make them cancel out, my chromium equation, I have to double the whole equation, so that I end up with 2 electrons. The electrons always cancel out. And so that's what this step 3 is to make the electrons gained equal to the electrons lost. And then you just bring your 2 equations together to get your net equation, which is 2 chromium ions plus the iodine, I2, which is a solid. And we go to the 2 chromium 3s and the 2 I negatives. The order that you write your reactants in doesn't matter to me. The order you write your products in, that doesn't matter. But you do have to have the reactants on the reactant side. You can always check to see that you're balanced. We have 2 chromiums, 2 iodines on each side, but the real check is that the charge is the same on both sides. So we have 2 times +2. So we have a +4 on this side of the equation because the I2 is neutral. And then over here, we have 2 times +3, which is +6, and then 2 times -1 is -2. So +6, -2, you guys count it on your fingers. You have 6 fingers, you take away 2. If you have 6 on one hand, it makes it easier. It would have made more sense, but you end up with a +4 on both sides. All right, so questions? We're going to do some stuff with this equation, then we're going to add dimensions to it. Sorry, I'm trying to see if I have another colored pen. All right, so let's go for it. We're going to talk about oxidation reduction. So redox is how it is read by chemists. The pictures, oh, my printer didn't print in color today. Anyway, the pictures of the redox everywhere is because one year I did this whole thing teaching, explaining. It was in Chem 104. And after a half hour of me doing, oh, it's like an hour maybe, a very sweet girl who was a good student just said, I understand the gaining, the losing, this, that, oxidation reduction, oxidizing agent, reducing agent. You guys remember that? We're going with this. She said, I just don't understand what the red ox has to do with anything. Now, she was actually from another country. And I just stood there. And so I do have a whole bunch of letters after my name, meaning I knew how to stall. And I just kind of looked at the class and took a drink of water because that slows everything down. And I turned and I looked at the board because I could not figure out. I thought, was she like on drugs? Why is she talking about redox? This is 20 years ago. And I suddenly realized that how I wrote this, because she came from their country, she read it as red ox, and she was taking it literally. Since then, actually, it's all over online. Like, this apparently has happened to all chemistry teachers, and everybody sees it as a red ox. So I have a couple of red oxes. One is in my office, and I need to go get because he'll be perfect for this. All right, so it is read as redox, but it does stand for oxidation reduction. We'll go to green. We don't call it an red equation, but whenever I write this, it's always taught as oxidation reduction. The historical definition was gaining oxygens is oxidation, and losing oxygen was reduction. That's why you were losing, so it was reduced. They then eventually realized there was more to it when electrons were discovered. So realized electrons are really only like 100 and some 20 years old. And they realized that oxidation, so the way I teach it is oxidation. I teach it, the reason the lion is over here, you can color him in, all beautiful colors. This is why your teacher tried to paint her face like a lion, but my skills are not great. I'm waiting for Janae's gonna come over here, right, and paint my face so I can teach tomorrow. I used to have actually horns. I had to give them back to somebody. I was thinking that would be great. So this is how I teach it. This is thanks to Dr. Russell, taught me this one. I used to use oil rig, which is a little bit boring, more boring, because to paint myself like an oil rig wouldn't have been fun. But I realized, I was thinking about this on my bike ride today, there's probably 6 different Chemistry 221 people coming from all different places. So however you learn this, you know it. Just, you're gonna see me doing it this way so you can kind of follow along. But or if you never got it, this is actually the best way I've ever seen to know it. This is how I do it. It works. Leo stands for losing electrons is oxidized. So that is, again, oil rig, oxidation is losing. And then GR is gaining electrons is reduced. And the reason it's a lion, so usually I have my stuffed Leo. So those of you who had 221 with me, remember Leo. He will be here hopefully by Thursday if I can get permission to go back to my office. It's just still so bizarre to me. I have to get permission. But if you were born at this time of year, you are a Leo. Is anybody here a Leo? Ashley, are you a Leo? Right, so you have to be petted. We have to take care of you like a cat.
Yeah, today is actually my birthday.
Is it really? Oh, we got to sing. You guys got to take your mics, open your mics up.
Oh boy.
Come on, Alexander. Harrison, you got to join in. Harrison, really? I'm going to take points away from you. He's like,
Oh, I
got
don't want my points taken away.
I can stop recording, but who really cares? Happy birthday
to you. Happy
birthday to you. This is great with the video lag. You hear it all at different rates. Happy birthday, dear Ashley.
Happy birthday to you.
It was great also because I didn't have to say what I didn't have to say what your name was because usually everybody pauses to listen to me. How old are you?
23.
Oh wow, congratulations. Happy birthday. And you did your class presentation also.
Yep.
We would have really been in harmony there with 12 different, like, the lag in the recording. That was pretty funny. I've never done that. So you gotta be the first happy birthday singing. Usually I like the Bunsen burner so you can blow out the Bunsen burner for the class. And anyway, so she's a Leo. So Leos are lion, so in the zodiac. And Leos do growl unless you pet them nicely, and then they just grrr. And so it's a wonderful acronym. You're going to see me just write Leo and GR often instead of oxidized reduced. And so our first equation, this is my Leo. So the electrons are on the product, meaning you're losing the electrons. Of course, on the final, it's not going to say what is your LEO. It's going to say what was oxidized. And then this is gaining, so the electrons are going in, so that's my GER. So again, it's just easier for me to write LEO GER. You can write oxidized, reduced. There is one more piece with oxidation and reduction. There's no questions with that. Rather than looking at oxidation numbers here, you can also do that. That LEO, the oxidation number always goes up. So we go from a +2 to +3. The iodine by itself has no charge, so it's a 0 going from 0 to -1. So its oxidation number is decreasing. But here we're doing half reactions, so you can actually tell from the half reactions without having to assign every single oxidation number. The other piece is there is something called, I'm going to write it underneath here, I abbreviate it as the OA, which is the oxidizing agent. And or the oxidizer. It is a reactant. These guys are reactants always because they cause something to happen. So they cause these electrons to exchange from the chromium to the iodine. And then RA is just my abbreviation for reducing agent. So the oxidizing agent is the reactant, the agent, the reagent that caused oxidation to happen, that caused something else to lose electrons. So the oxidizing agent always gains electrons. So your GER is always your oxidizing agent, and the reducing agent is opposite. So the I2 is our oxidizing agent. So whatever is your GER is your oxidizing agent. Your LEO then, your reactant side, the chromium with the +2 is your reducing agent. And this was a question Aaron asked me yesterday, and Jim, who's here, those of you who had me for 221. When I taught it, I would always write LEO GER, and then I would always write OA and then RA, and I crisscrossed. I didn't crisscross here. I just wrote next to the equation. You guys are going to have blanks to fill in, so it's just more that you have your method. We're going to do this with each of the equations as we go through them for the next 4 days, for next week, because again, those of you who had me for 221, I made a comment. I truly believe this is one of the 2 most important things that you learn in chemistry, is this idea of oxidation reduction. It is what drives our life, this movement of electrons. So we're going to see it shows up everywhere. In this chapter, one of the big focuses, though, is on batteries. And this picture here is actually the very first voltaic. This was volt, so it's a voltaic stack. Nobody's picked this as their demo, so if you don't like your demo, you can actually build these really simply at home. I've done it with the kids, and it's actually really cool. So there's a couple ideas like the lemon batteries or potato batteries. There's some really cool things you can do with some of those. So if you're listening and you don't like your demo or you don't have an idea, Google that first, see if you like how to do it, and then you can send me an email. So there are a couple of you who haven't picked a demo. And so if you haven't, probably like Wednesday, make sure we're in conversation about it. And then I'll talk about it more maybe tomorrow. Today you have your big paper and your presentations to worry about. All right, so we're going to draw a battery with this equation up here. And a battery always has 2 parts. It has an anode and cathode. So this first battery that we're going to draw, we're going to make it as 2 compartments. Just we'll separate the 2 compartments. So in a battery, there are 2 parts and they are separated. And you have to have an electrode. So that's an electrode. An electrode is some type of metal. If there is a metal in your equation, we do not have a metal in our equation. Metal would be chromium solid. This is chromium ion. You would use that metal. If you don't have a metal in your equation, you want to use a non-reactive metal, and that would be platinum, so I learned this. they have mined all the platinum there is, apparently. I know the Russians had bought all the platinum mines. In Montana had a huge deposits. And so there's actually been there always was, but there is a really huge increase on catalytic converters being stolen right now. Unfortunately, crime has also been going up, I've noticed. But I know several people have had theirs stolen in the past couple of weeks. So since we don't have a metal in our equation, and when we do, I will show you how to label those. I think it's the one we do tomorrow. So that's just the electrode. It has to be a metal because metals conduct electricity. So the whole point here is we need electrons to move around. So maybe you can write that. Electrons are moving. And when electrons move, we've learned how to tap into that. We have cell phones, we have lights. Having been in Nepal where we didn't have electricity, you know, writing in your diary by candlelight is really cute the first night, and then it gets really tedious. Having electricity is really nice. All right, so we're gonna write the half reaction. We'll do the chromium one first. So we have the chromium going to the chromium ion, the chromium 2 going to the chromium 3. And I'm going to write underneath, this is my oxidation, this is my Leo. We should show, right, plus the electron. So oxidation again is losing. So these electrons are going to be lost. These two are going to be hooked up together. We're going to make a wire. That's just my curlies because I have curly hair in case you can't notice. The electrons are leaving the chromium. So they're leaving the chromium. This is like a solution of something. And the electrons are going up the platinum through the wire, and they're coming to this side. And then this side would be our iodine. So we would have iodine crystals becoming iodide. And sorry, my electrons are being gained. This is my GER side. So reduction. All right. Questions up to that point? We're only halfway done. That's just taking the information from above. So we have to complete this. So a couple things. The anode is always oxidation, always. Remember that as we go through the week. So I'm going to tell you the cheesiest way that I remember this, and I don't know if it's because I'm a female. Anode starts with a vowel, and so does oxidation. And I never get it wrong when I'm teaching. I never have to think. The anode is always oxidation, no matter what type of battery we're drawing. The cathode is reduction. So this is where the whole thing of cations and anions is going to come from. So oxidation's over here. This is my cathode. And it makes sense. I have my cations, right? We'll talk about that more in 2 days. And the other side, GER, is always your anode. So you will have to label which side's your cathode, which side's your anode. And you will always show something called the polarity. So I'll write it down here. The polarity, it's not, we'll call it the charge, but it's not really the charge, it's the polarity. It's either positive or negative. The positive is the cathode, and the negative is the anode. Now, I want to make a quick comment here. Up here, I told you the anode is always oxidation. That is truly an always. Never said the word always here with polarity. It is going to be today and tomorrow, and you will see then on Thursday what's going to happen. So as long as we're drawing a battery, in a battery, the cathode is your positive. I've actually known that since I was a wee little girl, like this big, because my dad, like when we were changing batteries, was like, why is there a little plus on the one and the negative? And he's like, well, that's the cathode. And so when you have children, use big words because then they're not afraid of them. Children, like we're all children. You're a child until you're like 250 years old. So you're going to show this is the positive, this is the cathode. The electrons, it does make sense. The electrons are moving to the negative. And The other problem is this. I was going to do this in color and I forgot. The salt bridge. You have to complete the circuit. So the salt bridge completes the circuit. You know what? Did I just say that backwards? I'm looking at my picture and I just did something backwards and nobody caught it. Again, I apologize. I'm used to writing on the board, and if I could just do this all on the board, I would be 1,000 times happier. And looking here and looking on the computer screen is like my left and right brain just keep getting switched. So I said it correctly over here in the notes, and then I labeled this wrong. So oxidation is the anode. It's like, get rid of this teacher. So, right. I should copy on that. You all copied. Like little, really good people. Did anybody catch that? All right, so oxidation is the anode. Probably people at home are like, yeah, I got you. What were you doing? You're all sending me emails. And then this side, right, reduction is always the cathode. So my cathode is my positive. You gotta change your polarities. Boy, we should always use pencil, right? All right. So the chromium is our negative side and the iodine is the positive, and now it's going to make sense to me. We're going to draw a bridge. So the bridge is called an ion bridge because ions are going to flow. And I'm going to make them negative ions, which are anions. That makes this easier. Negative ions flow the opposite to complete the circuit of the electron. So our electrons are negative and they're flowing this way, and then to complete the circuit, the anions are flowing the other way. The anions, so you write it over here. That's why I caught myself where my mistake is. The anions always flow to the anode. So the electrons are always flowing to the cathode. So for simplicity, I did it as anions. You can actually also do it as cations, but cations have a positive charge, so they would flow the opposite way of the anions. So positive moving opposite would be the same as the anion moving that way, and it would also complete the circuit. And now your teacher did it correctly. Any questions? And I apologize to all of you at home watching along. All right. So, hopefully your teacher doesn't make that mistake again. All right, we're going to do this equation. This one's a little different because there's a whole bunch of oxygens. It's like, whoa, this equation up here was really nice. And the oxygens came up because you're either going to be in an acidic or basic environment. We're going to do an acidic. There's 2 extra steps here. So break it into the half reactions. So the MnO4, that is a negative charge. Anybody remember the name of that ion? Your teacher does. Permanganate. It's purple. It's really nice. You can do some really cool demos with it because it is a really good oxidizing agent. Spoiler alert. I actually can tell just looking at this equation, it's losing oxygens. Losing oxygens is reduction. It's a biochemist thing, and so we looked at it in terms of the oxygens instead of the electrons. And then my other half reaction will be, all right, let's try again. Anybody know the name of that ion? C2O4 with a -2. It's in Brussels sprouts. It showed up in like one of your homework sets about oxalic acid and Brussels sprouts. So this is the oxalate. That's what forms kidney stones. So some people get calcium carbonate kidney stones and some people get calcium oxalate kidney stones. So apparently if you have a kidney stone, you're supposed to pee into a sieve so that you catch it. And I don't know anybody who can do that because it's so painful. It's like giving birth to a watermelon, so they say, because that part of you is not supposed to get stones. All right. First step is you always balance the elements, not oxygen. Leave the oxygen for last. So I have 1 Mn. Here I have 2 carbons. So make sure you balance your other elements first. Save oxygen. So that's why it says here, elements except for hydrogen and oxygen. This order works beautifully, and it will just take practice. All right. Now what we do is we have to balance the oxygens, and you balance the oxygen with water. These are aqueous. So these are solutions that are always aqueous. So there's as much water as you want around. Oxygen, O2 from the air, is like the best oxidizing agent there is. That's where all this terminology comes from. Its greed for electrons is what drives our life. So you don't want O2 showing up in your equation. So I'm going to add 4 waters. It's really bizarre the first time, but then you get used to it. So there's 4 oxygens. I need 4 waters. But now I have 8 hydrogens, but we're in good shape because it's acidic. So we're going to do a no-no that I told you back when I started introducing. There is actually no hydrogen ions, it's hydronium, but that makes this equation really tedious. So we're going to go with the hydrogens. So just H+. I need 8 of them. So again, we balanced, we had 1 manganese, 4 oxygens, 4 waters, 8 hydrogens. And now my next step with that one is the electrons. So let's see if my red will work. Nope. I can use a pencil. Maybe this one will work. Over here I have a +7 because I have a +8 and then a -1. On this side I have a +2. So some of you are really good with positives and negatives, and some of you learned positives and negatives as puberty was happening, and there's sometimes the difference is 5 between +7 and +2. Which side do I put the 5 electrons on? It's going to go on this side. Because 5 negatives +7 will get me the +2. All right, so our first half reaction. Now let's do our second one. Balance the carbon first. So we did that. Now we're going to do the oxygens. Oh, what luck. It's done. I have 4 oxygens. So I have 4 oxygens, which means I don't have to deal with the hydrogens either. I do always now do the electrons. Last step. And this one's pretty easy. This side's neutral. That CO2 is a gas, and then the ion C2O4, we would need our 2 electrons on the product side to balance the -2 on this side. Again, your electrons need to end up on opposite sides. I'm having like PTSD from last year. It's the 4th week, and my class last year, some of the students, they got behind and they just never could get these electrons. It was most everybody got it, and they were like, got it. You got to spend some time doing these, going back and doing some practice. All right, our next step is the multiplication factor. So we're going to multiply 5 and 2. The lowest common number they have is 10. So we're going to multiply my top equation by 2. Do not show it like that. If you show it like that, you're going to end up making a mistake because you're not going to remember how to carry it through. So this becomes 10. Actually rewrite them. That becomes a 16. This becomes 2. This becomes a 2. And that becomes an 8. I don't actually recommend that you erase them. Just use a different color and cross them out. My second equation, I'm going to multiply by 5. The key to all of this is our electrons have to end up the same. So I'm going to have 5, I'm going to have 10, I have 10. The electrons have to cancel. That's what's determining how we multiply. And again, We're going to do some more practice today and tomorrow and the next day. We just keep practicing a few of these every day as we add on layers. All right, now we can add the equations together. The electrons are gone, and everything else we just pull down. So we have 16 hydrogens. Make sure you have your charges. We have 2 permanganates, 2 MnO4s. We have 5 oxalates, so that's the C2O4, -2. And then over here, again, it doesn't matter the order you go in, you have 10 CO2s, you have 2 manganese, and you have 8 H2Os. We're gonna do a quick check. Now, back in 221, you were taught very well by your teacher to go through every element, and oh my gosh, that would be so tedious with these. I just check my oxygens. If my oxygens are the same on both sides, and I check my charge. If they're the same, you probably got it. If they're not, it's usually take a quick look, but if you can't find your mistake, just erase, move on, and come back and do it with a clean slate. So I have 8 oxygens. So 2 times 4 is 8, and 5 times 4 is 20. So I have 28, and over here, my oxygens, I have 10 times 2, which is 20, and then plus 8. So 8 plus 20 and 20 plus 8, I'm pretty sure it's the same. I ran out of toes and fingers, but it's 28. All right. It's what Ashley will be 5 years from today. And ponder. You'll have this weird flashback of the class at this moment in 5 years, Ashley going, why am I thinking about that chemistry class on my birthday? And then she'll think how beautiful harmony we had. And she'll probably tell a story and nobody will get it. All right, let's look at the charge. So I have a plus 16. I have 2 times -1. Then I have 5 times -2, which is -10. So this side, when you add that up, is +4. You can do this with in your head. I'm going through it the long way because some people do struggle with this. Over here, oh, how nice. We have so many things that are neutral. We just have 2 times +2. We have a +4. Our charges balanced, our oxygens balanced. We're good. We feel great about this. Oh, except your teacher is probably going to ask you to either do Leo or to do GER. So let's do both. So while your teacher's trying to find another colored pen, I have like a whole packet of beautiful colored pens. Go ahead and do your Leo GER. Write down your anode, your cathode, and yeah. I don't know what happened. I've lost 3 pair of glasses in 3 weeks too. Things are somewhere in my house because we can't go anywhere else. All right. So what day is today? Today's 18th. So my first equation is gaining. So this is my GER. I'm going to lose that pen. This is GER. So that's my reduction equation, meaning I would ask you what element is, or what is oxidized, what is reduced. That's how the question will ask. It is an element that is oxidized, not the compound. It's not going to be oxygen if you have another choice. So don't pick oxygen if there's another choice, and there is. The manganese is reduced. It ends up as a +2. You can write it as Mn +2. That doesn't matter to me. That would mean the oxidizing agent is that equation. So the MnO4 negative would be my oxidizing agent. For reduction, my second one is losing electrons. And so again, don't pick the oxygen. So the carbon is what is oxidized. The carbon is yeah. So my reducing agent is the C2O4. So I'm gonna make a quick comment to Erin because we had to talk about this yesterday. I'm not crisscrossing. I don't know why. Again, it's probably because my brain is having trouble teaching on a piece of paper and not on a board. So I'm having to rewire a brain after 25 years of being able to teach this very well. We're gonna add one more piece. which is the anode, which is the cathode. Oxidation starts with a vowel, so your ox is always your anode. So my second equation, my carbon equation, is going to be happening at the anode. My reduction is your cathode. That's why I have the ox. He's here helping. All right, which one is the negative? Well, this is easy for right now. The anode is just like the anions. And the cathode, cats have paws. That does work with this. The cathode is going to be positive here. The electrons are going to be flowing. What is oxidized is losing electrons. So the electrons are flowing from the anode to the cathode. And then the anions would be flowing to the anode. So that's like a mini battery we just made there. You guys are going to get to draw batteries from me, like on Show Your Work, but on the final, you might just see a question where it has an equation. You get to do these on the final. There's one on there. So you'll have scratch paper. And believe it or not, everyone gets it. It's like the comfort zone on the final. Right now, it's not very comfortable, but it will be by the end of the week if you practice. Is there any questions before we move to the next page? I don't even know what to ask yet. All right, I'm gonna flip. Oh, look, you guys are gonna become proficient. So I'm gonna pause us. This may remind me to record again. I'm gonna give you guys like 3 minutes, try what you can. Split your half recording again. All right, welcome back. Did you all stop me? We're gonna do, I'm gonna see if my red pen works. I'm gonna split, you can keep writing. I'm gonna go ahead and split into my half reactions. I can do my half reactions in different colors. Here's my chloride to the chlorine gas. So that's always your first step. And that, usually everybody gets at least that. Before you go crazy with stuff, make sure before you start doing the oxygens, balance your chromium. I will tell you 50% of the students, having done this for as long as I have, they forgot that step, which makes nothing work out. Now we do the oxygens. So 7 waters on the product side gives us 7 oxygens. That now gives me 14 hydrogens. And that wasn't so bad. Now we have to do the electrons. Over here, oh, let's see if the orange works. That won't show up. We'll do it in purple. We'll do it in green. I have a plus 12, a plus 14, and a minus 2. Over here, I have 2 times 3, so I have a plus 6. And the difference between the 6 and the 3 is, I'm sorry, the 6 and the 12 is 6. Which side do the 6 electrons go on?
The left side.
The side that's going to have more positive, because we're adding the negatives. So on the reactant side. So yes, so that would be our 6 electrons. And again, having done this for as long as I have, some of you will struggle with that initially. You just have to practice, and you can always go and check it. All right, the second equation is actually pretty straightforward because there are no oxygens. We just do our 2 chlorines, and the 2 electrons will go on this side. Now, you can always do the easier equation first because the electrons, if they're on, we're losing electrons are on the product side. The other one has to be gaining them. We can do our Leo GUR at this point. So my first equation is, again, my GUR. It's just coincidence. Don't make that. It's gaining. The electrons are going into it. If it's reduction, then my second equation is my Leo. that is nice to label these, because when we draw our battery down here, that will help. All right, our electrons have to balance. So the number we need to get to is 6 electrons. My first equation is good. My second equation, I'm going to multiply by 3. So 6, 3, and 6. Cross out your electrons gently so you can still see them. You can buy those erasable pens now, so you can use different colors that erase, and then we just bring it all together. So 14 hydrogens. You've got to show your charges. Some of you in the KSP got a little lazy and didn't show charges. There are 6 chlorides now. And again, the order you write the products in doesn't really matter. However, I want to add a piece with that. It doesn't matter. Traditionally, though, the hydrogens and the waters are shown first and last. So because they're the additional piece, and that makes it, that's how you're going to always see me do it also. So that's a good habit to get into. The hydrogens are not always on the reactant side. That's just a coincidence of the first 2 I happen to throw here for us to do. We're going to do a quick check. Let's check oxygens first. So I have 7 oxygens on this side, and on this side I have 7 oxygens. So my oxygens are good. Check our charge. We have a -2, and over here, and a -6, so I have a -8. And on my product side, and a +14. So I have a +6. Sorry about that, which makes sense. So I have +14, -2, -6, which would be +6. And over here I have a +6. So we're good. Again, you don't have to walk through every element. Just check your oxygens and your charge. If they're not, just keep going. If you don't see the mistake, if you're in a time situation, don't dwell. We're going to draw the battery. I'm going to show you a slightly different way to draw it. You will see it. I recommend, I'm going to draw it still the way we did. You will see where they will draw one piece and they will split it into 2. I don't like this way because of where we're going. I like to have them split into 2. So in a battery, they are split, and you put it in your flashlight, and that helps to complete the circuit. All right, let's go ahead and write you would write your full half reaction in there. Usually the ones you're drawing the battery of are the simple ones, like the first one. Oops, we have our 6 electrons, our chromium, 7 waters. And this is my reduction side. I like to label it at the bottom, so this is my cathode. And you can write your half reaction in the other side. So again, listening at home, pause me and make your battery. So I'm just writing my 2 half reactions. Another really common question that is asked, it doesn't matter which half reaction's on the left and which is on the right. I'm just randomly pulling one into each side. It is not that the oxidation is always on the left or right. Oxidation is always your anode. You always have to have them separated. So somehow there is a wall here. That's why the first time I drew it as 2 separate compartments. So it's up to you if you want to draw one and separate them. You do need to put your electrodes. Again, we don't have a metal. That must show up tomorrow. Anode is negative, so you always write on it the polarity. So that positive negative is called polarity. And then you also, in this case, I'm going to write PT, so I'm going to use platinum. Platinum and palladium are considered the noble metals. That's why they're so valuable, because they do not react. And then you have to make your wire connection. You can make your wire as fun as you want. So my electrons are flowing that way. They're flowing the wrong way. My arrow was there already. The electrons are flowing to the cathode. You do need to show an arrow with your electrons. That was, my arrow was from before. All right, there's one more piece. Anyone know what I'm missing?
Is it the salt bridge?
Yeah, we have to complete the circuit. For this to work, you need to complete your circuit. Now, you can just draw that simple bridge, or you can have a lot of fun. So, by the way, speaking of fun, I didn't give myself enough room. If I mentioned I really miss using a board because then I have all the space. But you can make a bridge. You can make it like a brick bridge. You make a guy, you can make a guy fishing on the bridge. He's fishing. There's a guy down, there's a little fish down here saying, oh, look, this guy's fishing. I have a guy in a kayak down here rowing, or they can be in a sailboat. See my drawing skills. So a lot of you commented on your QA lab that your drawing skills were lacking. You guys all have amazing drawing skills, and I want to say, like, thank you. People did really fun flowcharts, and so this morning that was actually the first thing I saw. Was I went into the grade book and I just went from one flowchart to the next, and just they were beautiful. So thank you. You do them again on Thursday. It's going to be a QA3 lab. It is a bigger flowchart. There's 8 steps instead of 4. So you're going to probably want to make a sketch, and then you can have whatever fun you want. All right, the anions are going to flow in the salt bridge towards the anode. And my cat Rocky just went to sleep, but if you want to draw a cat instead, the cat would walk the other way towards the cathode. So if you want to draw a cat, he would have to be walking in that direction. I don't have enough space. I usually make sharks in guys drawing. All right, any questions? It's really good to like just be playful. There's our battery. So I don't know, you've heard of alkaline batteries, like AA and AAA batteries, C's and D's are alkaline batteries. We're going to get to that tomorrow. These would be acidic batteries, like your car battery. It's acid-based. So I'm pretty sure all batteries, well, they have to have some kind of solution. They're usually either acidic or basic. There is, you can look in the book, there's a whole explanation when it's acidic and when it's basic. You don't have to worry about that. You're going to be told it's in an acidic environment or it's in a basic environment. That's an alkaline battery though. All right, we're going to do one more thing with this. We're going to talk about something called cell potential, or the E of the cell, capital E. It's also known as the EMF, electromotive force. I think that's funny because I see EMF and I think the electromagnetic fields that we talked about. I can't remember who I was talking about, but why you should have your cell phone as Brianna. Your cell phone has to be turned off at night, or at least in airplane mode, because the electromagnetic fields do interfere. You can't actually produce melatonin if you're doing stuff on computers after 10 o'clock at night, they have found, and that's why our sleep patterns have become funky. All these people are like, I can't sleep, I can't sleep. Turn off your phone. With that, you got a lot of you are pretty young. I think yours is shifted because you tend to go to sleep later. All right. So there's a lot of words on this page. It is a measurement in voltage. Voltage is flowing charge. So like water flowing, this is charge or electrons flowing. It is the force of that. There is, at the end, the last page of your notes is a table, of course. If you haven't noticed, you know, we used to have the book, students were like, what are all these tables in the back? Oh, they're for Chem 223. We go table crazy. I just took the simple table. There are really elaborate tables online. It is a hierarchy of what takes electrons from what. Somebody sat there, they figured this out by making a whole bunch of batteries. There is a hierarchy on the table. Those of you who had me, you should not be surprised by what is at the top of the hierarchy. The greediest element of them all, the most electronegative. In the talk Margaret gave today from Linus Pauling, when he made his chart on electronegativity, the most, did you turn the oven on? No?
No.
Okay. I had something in there. Sorry. Fluorine is the greediest of them all, and it is at the top of the chart. So this is a chart of greed. Who wants electrons the most? And so they're all gaining electrons, and it goes down to the least greediest. So these would be like the Gandhi ones, so they're giving away. So lithium, which makes sense, the metals do not want to gain electrons, they wanted to give them up. And so they're at the bottom of the chart. All right, you're always going to have a chart in the test. In the final, it embeds a mini chart, and you'll see that like in your homework, there's going to be some questions with the mini chart. So we're going to find R2 that we're doing right now on this chart, which is the chromium. The CR207 is right here, kind of towards the top. Oh, a couple comments about the chart. The chart is always reductions. It only shows reductions. And that makes sense. In our piece here, the chromium equation was the reduction. It is shown just like it was on there, except they're showing, opposite what I told you, they're putting the hydrogens there. Our second equation is the chlorine, which should be right above it. And the problem you'll see with the chlorine, I can show on the chart, it is flipped from what we wrote. We did it correctly, and the chart did it correctly. So what we're going to do is we're going to take from the chart the numbers. So the chromium was positive 1.33 volts. So you're just reading straight across. The chlorine, before you write it down, we have to flip the equation. One of them always gets flipped. The book teaches this different. I don't like how the book teaches it. People get it wrong. We're going to do it just like we did with delta G's. When we flip the equation, what happens to the sign? You change the sign. This is all about positives and negatives. So we're not flipping our heads upside down. We're changing the sign. So one of the half reactions always gets flipped. So the chlorides. So this becomes a negative 1.360 volts. So it was flipped. You change the sign. We're going to go through all this again tomorrow. So I redid the notes, reshuffled everything. So I'm showing you how to write the equations, the batteries, and how to use this chart. And then tomorrow we'll do more practice with it, and again on Thursday. So this becomes really deeply ingrained. And you're just like, this is great. No mice charts. All right. So all you do, it's just like what we did with delta G's. You add them together. So we would just add this up, and we get, oh, you know what? I made a straw battery. I can't believe this. I get a negative 0.03 volts. That's my E of the cell. You'll often see it E net. The chart is standard, so they put a little 0 there. That little not sign just means using the chart. Reminder, what are standard conditions? Well, the only one we really talked about was temperature is 25 degrees or 298 Kelvin. The other thing is everything is 1 molar if it is aqueous. And then if you have a gas, which we had our one gas here, the chlorine, it is considered to be 1 ATM. I'm going to keep it as ATMs. It is technically, I think, bars, BAR, which is pretty much the exact same thing as an ATM. So whatever unit, you're just going to keep it in that unit. We're going to get weird units here because things are going to mix and match. We're not going to do gas law stuff. Gases stay in ATMs, aqueous stays in molarity, and we'll see that. By the way, I put a little fun fact there. It's something you use in physics. We're not going to use that here, but an electron is not actually -1 charge. It's just we assign it a -1 and we make a proton a +1. Charge is actually technically measured in coulombs. Oh, look at that exponent. It's like so bizarre sometimes when you start looking at the exponent chemists and physicists use, because none of this is real, right? That's why the whole quantum world makes more sense. All right, we're going to walk through. So one of the equations you flip, you change the sign. So 1/2 reaction, you have to change the sign. You don't change my half reaction on the chart. I'll say flip on the chart. That means you change the sign. So if it was a negative, it becomes a positive, and then you just add them together. Again, I teach this different from the book and from all the sites online. You can do it their way if you want. All right. So some wordy notes. You don't really need to know this, but the chart is always reduction. Reduction means you're ending up reduced. So it's going from oxidized to reduced. This number 2 is what I just talked about. When you flip the equation to change the sign, just like what we did with delta G's, delta H, delta S. The higher the E value at the top is the better oxidizing. So if these are all reductions, these are all oxidizing agents. And it makes sense again because that's where the halogens and the oxygen are. And then number 4 is the other one that's really important and where we were moving with this. If you get a positive E, it is product favored. It's going forward. That means it is spontaneous. And that is a battery. I'm like, this can be the question for those of you who listen to my videos, which can be you guys too. So did we make a battery up there? Is our battery going to work? Any of you guys? Your teacher just picked a random question and I had never done all the math before. We got a negative. This is non-spontaneous. So our battery is like not going to happen. Everything's going to actually flip. The electrons are actually going to go the other way. So, or you put a big sad face with it. But that's the email you get to send me. Why it doesn't work? Because we ended up with a negative cell potential. So when you do the homework, when you do a question on the worksheet, when you do a question on the test, whatever you get, you go with. If it comes out negative, it just means it didn't work. It had to go the other way. So same like what we were saying, if we flip the whole thing, so if the electrons moved the other way, our chlorine was our cathode, we would get a positive 0.03. All right, last piece on this page is also important, and it will make more sense when we do the math. It is an intensive property. So again, if you're having trouble falling asleep, go ahead and Google intensive versus extensive. And it will make sense for that moment, but all you need to know is when we're doing the math, it's concentration dependent, not quantity dependent. The electrons have to cancel out, but then you'll see as we're doing the math. I'm going to move on. We're going to do one more page. I think I have time. Yeah, because this page is pretty simple. You need your chart. What I want you guys to do, we're going to do the first one together, and we're going to put it with this piece down here. So you're going to write your 2 half reactions. Oh, and this will be where I can explain that little note at the bottom. So aluminum solid, I like to, when there's a state of matter, I like to write it in. The ion, I show the charge. All right, gaining or losing electrons. My electrons have to go on this side, and there's going to be 6. There are 6 electrons, because 2 times the plus 3, and so this is my Leo. We're not drawing a battery with this, so, all right, and then my other half reaction is the tin 2 going to the tin solid. My 6 electrons will be on the other side. That's why this one was already had the 2s and the 3s, because it already, I'd balanced the electrons for you. So that one is my GER. All right, so we go to the chart, and we find them on the chart. So aluminum is going to be at the bottom. Your 1As, 2As, your fixed charge cations are going to be at the bottom. And how it's shown is the aluminum gaining electrons. On our question, the aluminum is losing. So we want to flip the number from the chart. So on the chart, it's a negative. So on here, this E is just in a different color. Positive 1.66 volts. It's a little Energizer bunny. Sorry, when I put my hand under that light, it always does that. All right, and then we want to find the tin. Be careful with the transition elements. The ones that have variable charges, they show up multiple times. So I will show you. There is tin as a 4 charge going to a 2. That is not what we did. We did a 2 charge going to tin solid. And this is written as our half reaction, so it's a negative 0.14. All right, that last comment on the previous page where I said it was an intensive property, concentration matters, but not quantity. The fact that we had to triple this equation does not change the E. So you do flip signs, but you don't multiply by any factor. So even though we multiply this by 2 and this by 3, you do not do that to the E. That is the piece that is different from when we did it with delta G's and delta H's. Now we just add our two numbers up, and our E of the cell, or E net, is going to be a positive. I always show the positive because that means it worked. 1.52 volts. So this one is spontaneous. It worked. This will be a battery. All right, I'm going to skip down, and we can come back and do the other ones if you like, or I can give you the, yeah. Or actually, no, you know what? We're going to do them because I realized something came up there that I want everybody to know because it will show up again. All right, the 2 chlorides go to the chlorine gas, and the Br2 liquid goes to the 2Br. So the comment I was trying to make on the previous page, when I give you an equation, like on A and B here, you have to go how I wrote the equation. We put our electrons, the chlorine is losing electrons, the bromine is gaining electrons. So the bromine, when you look on the chart, it is going to stay how it is. So the E is 1.08 volts. So again, on the chart, the bromine plus the electrons, I just picked its number. The chlorine, we flipped because it's going the other way. So it's going to be a negative 1.36 volts. Right, you can already see when we add these together, our E of our cell is going to be negative. Is that right? 2.8 volts. So that just means it is non-spontaneous. This will not work as a battery. It would have to go the other way. The top one was spontaneous. So again, when I give you the equation, whatever you get is what you get. You can get positive or negative. How that's different is on C. I did not give you the equation. And actually, I want to go back. Well, actually, I'll show it on this one. You have to make it work. So it will say, make this one work, which means we have to end up positive. So we're doing zinc and nickel. So looking at the chart. Again, the nonmetals are at the top of the chart. Zinc is right there. And nickel is above it. When you have the chart and you are asked to make it work, whatever one is higher on the chart is the one you keep how it is. So you're going to write the nickel how it is nickel 2 plus 2 electrons. Oops. Sorry. And while we have it, we'll write its number. The E is negative 0.25 because we didn't change that one. The lower one is the one you always flip. So the zinc solid becomes your reactant. The zinc ion becomes your product. And the E, we change the sign. So it was negative. This becomes a positive. And we add them up. So if you flip the lower one, it will make the answer always positive. Again, it has to do with how I worded. I did not give you the equation, so then you're making it work. I wanted to mention one other thing about the chart. The chart was made based off of hydrogen. All right. These numbers are made up numbers. So in case you never realized, the chart Margaret showed today in her talk on electronegativity, Linus Pauling made up those numbers. He just said, let's just make up numbers. We need a chart. All numbers are made up, right? So somebody said, let's call this 1, 2, 3, 4, 5. So somebody said, okay, let's call the hydrogen cell 0. That is standard. And then they made up a whole bunch of little containers, and then they compared things to hydrogen, and they got these numbers. And so they made an arbitrary code, and that's what we got. That will come up again tomorrow. This is just to get it in there the first time. You should all be having questions. And you can see your teacher made a mistake. Oh, I made a mistake twice. They emailed me about my mistakes. All right, last piece is putting it with the entropy and free energy. So delta G is free energy. I do not know why they called it free energy. Nobody picked Gibbs as their famous person, and anytime somebody does, I still don't understand. I don't know if they do. E is the cell potential. That's what we're learning about. N, little n is moles. Remember gas laws? However, this is all about electrons. It's oxidation and reduction. It is moles of electrons. So remember in that very first one, we doubled the aluminum, and I said you do not double the E. This is where the 2 will come in. Actually, the 6 will come in. So this electrons that cancel out, that's where the number finally comes in. You don't do it up here, because then we'd be double dipping and it would come out wrong. So the moles of electrons is the electrons that canceled out. So like on this last one, the nickel and the zinc would be the 2, or that would be the 2. All right. So we just have one little piece left, and that's the F. the correct way to do it is it's actually a really fancy F. You guys can make, wherever you make a fancy F, you can make it a normal F. I've seen it all different ways. This is named after, I'm going to flip through my pages real quick. We're going to talk about him in a couple days. I can't remember who's talking about him, but there he is, Michael Faraday, who gave us electricity. And so Faraday's constant, he did not name it after himself. This man was extremely humble. And it is in coulombs. A coulomb is a charge of an electron. So going back to this page, Faraday's constant is 96,500 joules. What are we doing? Let me think. Sorry. Why I just did it wrong. I had my mind on something else. It is per mole of electrons. Coulombs, sorry. I said it before. We're going to get to joules in 2 days again. No, it was joules. It is not. It is what is cell potential. Cell potential is in volts. I apologize. I'm talking in circles. That V, the unit is joules per coulomb. That was on the previous page. I'm having to bring brain cells, connecting them from a year ago. And so you guys have all gone through that. You guys, for your final, just have to find brain cells from like the past 6 months or right back to 221. And we'll do reviews, so you won't have to stand here in front of a camera and feel like a fool. So that's the unit of a volt, is a joule per coulomb. This is Faraday's constant. We're going to use it a lot over the next 3 days, so you'll know it. Or you can put it on your little note card. So when you do your test, you have a little note card with the pieces you need. But if you do it enough, which if you do all your work and don't just copy it, so what we're going to do is, it is a way, if you have cell potential, that you can find the free energy change. And we're going to do the first one. So you're going to always state the formula. There is a negative in here. You can write your F however you want. Those little knots just mean where it's standard. So if I do the first one, I have 6 electrons. You can just write Faraday's constant as the F, or we can write the number in so you learn it. So it's coulombs per mole of electrons, or you can just say electrons. This 6 is technically 6 moles of electrons. And then our E, 1.52, rather than writing in volts today and possibly tomorrow, let's write the unit in, joules per coulomb. Now, there was something I said the last 2 lectures with entropy and free energy. You're going to get a really large answer here because Faraday's constant's huge. Voltage are actually really small numbers. They're in joules. But delta G's, delta H, delta S, they're huge numbers. That's why we have global warming in the combustion age, because you get a lot out of them. So you're going to want to change your joules to kilojoules. So we're going to want to divide by 1,000. And I have a calculator somewhere. I have an answer key somewhere too, but I found the calculator first. We didn't have to do. All right, so we get negative 880 kilojoules. You will then be asked, does your answer make sense? And it does. If E is positive, delta G is negative, that means spontaneous, which means product favored. You don't have to give both things. I'm writing it down because some people, it makes more sense to say product favored. And some people, like your teacher, I really like that word spontaneous. Like deciding to paint my face like a lion, because lions growl because they're purring. So if we do the second one, what kind of delta G will we get, positive or negative? Well, if E is negative, delta G will be positive. I'm looking to see if my answer key is handy so I can give you guys numbers. No, of course it's not. All right. Go ahead and punch, I am punch them all in. When you do the second one, your electrons will be 2. So on B, so this was A. For B, I got, my decimal place is off. Yeah, sorry, you'll get a positive 54.0 kilojoules. So this one was non-spontaneous or reactant favored. So delta G was positive because E was negative. So it does not work as a battery. And then for C, what do we have? 5, 1, 3. We had negative 99 kilojoules. And that again means spontaneous. So last question. This should be the one you have to like send me the email. Here we go. Can make you send me an email. You have to send me one email with 2 answers. It really worked for this bonus point. So here we go for you guys for a bonus point. But Harrison, you have to like sing the alphabet backwards before you can answer. So you guys ready? This is like double jeopardy. What will the K value be? You don't have to give me a number. You can just tell me how will K be related in each one of these examples. It all goes together. So if E is positive and delta G is negative, K is going to be, we should let Ashley have this. If you want it, Ashley. K going to be?
K would be positive?
K would be, we're looking at the number 1. It's going to be greater than or?
It would be greater than 1?
Yeah. She definitely deserves a bonus for having to listen to our harmony. So, and thank you for answering it the way you did, because I wanted to like kind of put this caution out there. E's and delta G's can be positive or negative. So they are compared to 0. They can be greater than 0 or less than 0. K's are always positive. It's their exponent. So K would have a positive exponent. K is a ratio. And so K is greater than 1, meaning you have more products than reactants. And then, of course, on B, K would be less than 1 because that would be non-spontaneous or reactant favored. That all goes together. So it kind of brings, this is a really cool way, it brings everything we do this term all together. It's why we come back and do oxidation reduction and thermodynamics, because it does have a relationship to equilibrium. All right, that's all I got. If there's a question, or I'll stop recording. And those of you at home, you have to email and put 2 pieces in that. And those of you watching, you can email too if